So we will look at the database internals chapters in a series of videos. Database Internals by Alex Petrov. Part 1 is about storage engines, and then part 2 goes into distributed systems. So what is a storage engine? The storage engine or database engine is a software component of a database management system responsible for storing, retrieving, and managing data in memory and on disk, designed to capture a persistent long-term memory of each node. Example of a storage engine would be LevelDB, RocksDB, WiredTiger, InnoDB, etc. So chapter 1, let's start with introduction and overview. So we have the DBMS architecture diagram is right over here. We can see there is the client communication, then going to the query processor, query parser, parses the query optimizer, optimizes the query plan. Then there is execution engine, and the execution engine also talks to the then storage engine, which is responsible for whatever we talked about. Additionally, there is other components in here, like there is a lock manager, transaction manager, buffer manager, and recovery manager. So many things are there. This is the architecture of a DBMS system. So memory versus disk-based DBMS. I have not really worked with memory-based ones. But yeah, there is a section on durability in memory-based storages, which employs some kind of sequential log file. There's snapshotting, there's checkpointing. Then there is a talk about column versus row oriented DBMS. Row oriented one stored the row together, column oriented one stored column together. Postgre is row oriented, column oriented stores. Yeah, there is a few of them here: C store, Vertica, etc. which have not worked in the past. Column oriented stores are a good fit for analytical workloads which compute aggregates such as finding trends, computing average values, etc. There is a section on distinctions and optimizations. To decide whether to use a column or a row oriented store, you need to understand your access patterns. If the read data is consumed in records and the workload consists mostly of point queries and range scans, the row oriented approach is likely to yield better results. If scans span many rows or compute aggregate over a subset of columns. Okay, so we are thinking about the case where we are not really scanning a group of, it's not a range and it's not mostly points. So, but we are scanning many rows or we are doing an aggregate, then it is worth considering a column oriented approach. Wide column stores, column oriented databases should not be mixed up with wide column stores such as Bigtable or HBase. These are wide column stores. There are actually, these are slightly, they are not, they are not column oriented databases. So in Bigtable or HBase, data is represented as a multi-dimensional map. Columns are grouped into column families. Column families are storing data of the same type, and inside each column family, data is stored row wise. And if I remember, basically Bigtable employs an LSM tree based approach with these SS tables, SS table compaction, etc. So there is a in-memory tree, binary tree, B tree, some kind of tree of a limited size, which keeps ordering of your key values, and it gets populated, and then as writes are coming in, these are optimized for a lot of writes, and at some point their size grows, so a part of the tree is basically taken, or maybe the whole tree is taken, and a new SS table is written. These are already, you can do a quick traversal and produce a file, a sorted file. So that is your sorted strings table, SS table. So you write it. So likely what is happening is that each column family, the data is together, and there would be, let's say, a mem table, which is your in-memory tree structure, and then there are these SS tables, right? So it would be optimized for range scan, right, and all the columns in the column family, you can basically find the data together. So in that way, the data is stored row wise. So yeah, it's a little bit, I think, this detailing required to understand what's going on there. While it is useful to understand the conceptual representation of wide column stores, their physical layout is somewhat different. A schematic representation of the data layout in column families is shown. In each column family, the data belonging to the same key is stored together. That's what I talked about. Okay. Next section, data files and index files. So data records are stored in data files, and then indexes are auxiliary data structures which allow you to efficiently locate data records. Right. Data files, sometimes called primary files, can be implemented as index organized tables, heap organized tables, or hash organized tables. Okay. So index organized tables are basically, there would be, I think this is the B tree based approach. Index organized tables, IoT, store data records in the index itself. Since records are stored in key order, range scans can be implemented by sequentially scanning its contents. Okay. Then heap organized tables. So it's just like a heap. So as data comes in, it is written sequentially. They require additional index structures pointing to location where data records are stored to make them searchable. And hash organized tables, records are stored in buckets, and the hash value of the key determines which bucket a record goes to. So these are the three kind of organizations of the data files. When records are stored in a separate file, index files hold data entries, and these data entries are uniquely identifying the data records. For example, we can store file offsets, sometimes called row locators, locations of data records in the data file, or bucket IDs in the case of hash hash files. What's an index file? A structure which organizes data records on disk in a way which facilitates efficient retrieval operations. Index on a primary data file is called a primary index, and index built on a set of other keys. All other indexes are called secondary indexes. Secondary indexes can point directly to the data record or simply store its primary key. A pointer to a data record can hold an offset to a heap file or an index organized table. If the order of data records follows the search key order. This index is called a clustered index. This is when typically we will have two columns, let's say, which are put together to create a secondary index, and one of the columns, maybe the second column, is providing you the sorting order, so sorted on date or something else. That is a clustered index. Then here is a section on primary index as an indirection. So different opinions in the database community on whether data records should be referenced directly or via the primary key index. Okay. Section on buffering, immutability and ordering. Buffering, this defines whether or not the storage structure chooses to collect a certain amount of data in memory before writing it to disk. And they note that of course every on-disk structure has to use buffering to some degree, since the smallest unit of data transfer to and from the disk is a block, and it is desirable to write full blocks. Then what about mutability or immutability? This defines whether or not the storage structure reads part of the file, updates them, and writes the updated results at the same location in the file. Immutable records are append only. Once written, file contents are not modified. Often the distinction between LSM and B trees is drawn as immutable against in-place updates storage. But then they note that there are structures, for example, BW trees that are inspired by B trees but are immutable. Okay. Ordering. This is defined as whether or not data records are stored in the key order in the pages on disk. Storing data out of order, mostly in insertion order, opens up some write time optimizations. Okay, so that was chapter 1.